Okay, good morning to all of you. I think we should start now. So again, during the session, if you have any doubt, you can just unmute yourself, or you can just put your comment in the chat box, uh, so that we can discuss on that query, and then we can move ahead. Is my screen visible to all of you? Yeah. Okay. Thank you. So in today's session, we'll just start with one more very popular and revolutionary generative model that is called as diffusion model. So we will learn that how diffusion model is nowadays basically used for generating the data, especially the images and videos, and how this particular model is different from the approach which is being followed by the GAN models. So just see the images, just see the beauty of these images. Uh, it seems that these images has been captured by very uh, high quality camera. But as a matter of fact, these images has been generated by AI, and one of the tool that has been developed by OpenAI, that is called DAL-E2. So all these images has been generated by that particular tool. We can also visualize that the quality of the images which has been generated by this particular model or this particular tool that has been given by OpenAI is much better as compared to the traditional state-of-the-art models and the vanilla GAN that has been given by Goodfellow 2040. So before going into the details of the diffusion model, I will just give you a clear-cut detail in a nutshell about the entire process first, that what is basic approach of the diffusion models, how diffusion models are basically able to create the images and videos which are very realistic, having the quite good quality as compared to the other conventional models. And because of some reasons, in terms of positive way, these particular diffusion models have basically uh, gained significant popularity in the past several years, especially after 2020. Because some of the papers which have been released in 2020 have become very popular, and then a lot of modifications were made, and nowadays we can see that Google, OpenAI, and a lot of companies like Meta have developed their own diffusion based model to generate high quality realistic images and videos. So naturally, what are diffusion models? They are used to generate high quality data, maybe image, video, text, audio, or something else. But especially they have gained much popularity for developing realistic videos and images. How they work? So I just want to give a recall about the generative adversarial networks, that how they work. Basically, GAN started with for noise. And what was the approach? We were having neural networks. One was G and one was D. G was starting with a pure noise, which was not getting. Talking about vanilla GAN, original GAN, which has been developed by the Goodfellow in 2014. Z started with pure noise. G means a neural network, nothing else. And initially it was a simple multi-layer perceptron network. DC GAN, later on we have used deep convolutional neural networks in case of simple MLP. So they started with pure noise, and we were not giving any kind of input from the original image that this kind of image I want to generate. We were not giving any kind of help to this network that is called as Z. They started with the pure noise, and they started discriminating that whether it is real or this is fake. And then the approach was the main approach was the voice is breaking. Just a minute. Now is it clear? Okay, can anyone just okay, it might be possible because of fan the voice was breaking. Okay. Okay, the basic idea of the network was to train the model in such a way that G is able to mimic the probability distribution of real data samples, that is called X. So my intention was to have a model, to have a neural network model, and to train that model starting from noise and to progressively learn the actual data distribution that is called as P data of X. This was the actual probability distribution of the data, so that it can generate the images which are very, very close to the real images. Here in the case of diffusion model, we have the same objective, and the objective is same, that we have to generate the images or text or videos, the data, such that it is very, very close to the real data. We have to generate the fake data which is very, very close to the real data. But approach is something different. What is approach here in the case of diffusion model? We start with, let's just see this image. I'm going to give the nutshell of the entire working of the diffusion model with this image only. And after that, we are going to get into the deeps of mathematics behind it, and what is our approach, what is our objective to train a diffusion-based model, to develop a diffusion-based model. The idea is a little bit different. What we do, rather than starting with the original noise, pure noise, we just create noise. We just create noise. I told you in the case of GAN, G network get the input which is pure random noise, that is generally the Gaussian noise. And this Gaussian noise didn't get any input, from the training data. We are not giving any kind of input from the training data or the labels in the original GAN. But here in the case of diffusion model, the training data is not pure noise. We are creating the noise. And how we are creating the noise? We are creating the noise by the input training data. Input training data. And how this noise is being created? Systematically. So we can say that this diffusion model D works in two phases. One is the forward phase and one is the reverse phase. The forward phase, we used to create the noise samples. How we used to create the noise samples? See this image. We have this input image, and what we are actually doing, we are adding a little bit noise in the original image. For example, the image at any time stamp, we are taking any data sample X, and this 0 represents the timestamp of the data. That means image at timestamp t is equal to 0 is this. This is the original image. and we want to create the images similar to that images, similar to the image that we are giving, and we want to create a model for that. So what I am doing, I will add a little bit noise to this original x plus, for example, beta, and I'm saying that beta is the amount of noise that I want to add on this particular image. So what I did, I just added some noise, and you can see that this image that is called x1. X1 means image at timestamp t is equal to 1. Is something which is not very close to the real one. It is somewhat blurred. And why this image is being blurred? Why? Because we have added some noise to this particular image. Again, in the next step, what we did? We again added some noise that is called as beta 1. So this image will become this x2. What will be x2? X2 will be x1, means previous image, plus some noise that is called as beta. You can assume any variable by which we are adding some noise. Again, what we are doing? Again, we are making x3, and x3 is equal to x2 plus some noise that is called as beta. So iteratively, we are doing the same thing. We are adding the noise to the original image. So the question is B or beta is fixed for every step? Not. It is not. I will tell you in detail about how B is varied by the course of iterations. So don't worry. So we can have a number of ways to add the noise. So for example, in the original paper, uh, who has developed the diffusion model, uh, have actually varied B linearly. We can just vary B exponentially. We can have some sinusoidal kind of function to add the amount of noise with the course of iterations. So this is not a constant. Okay. So again, x3, and again what I will make, x4 is equal to x3 plus beta. I'm assuming that beta is some variable by which I am adding the noise. So what will happen? For example, I have gone through 1,000 number of steps. After 1,000 iterations, this image is going to be a pure noise. Why I am saying that this is a pure noise? Because you can see that after 1,000 number of iterations, the image is looking like this, and you are not able to see any significant features in this particular image. This is the reason I am saying that this is a pure noise. And this is the forward step of the diffusion model. So what I told you, that this diffusion model will work in two phases. One is the forward phase and one is the reverse phase. In the forward phase, what we are adding some amount of noise that is called as beta. Here I am added beta 1, here I am added beta 2, here I am added beta 3, and so on. By adding the noise in the each step, what we did, we have just corrupted an image in order to make a complete noise. And we are done with the forward process of the diffusion model. Now what I need to do, this diffusion model has got the input noise, and it needs to produce a realistic image again. Equality, realistic image again. Now the question is, what is the idea and how we have to produce the image which is very, very realistic and high quality in nature from this particular noise? Okay. Now we have to go to the reverse process for the same in order to again get this get very realistic image from this particular noise. Then what I will do? One thing can solve my purpose. Which thing? If I want to get this image back, which thing can solve my purpose? That is the remove noise. Exactly, remove noise. And for example, if I am just saving that, what this is the amount of, if I am saving the value of beta 1, beta 2, beta 3, beta 4, beta 5. So if I am just saving the value of noise that I have given at each step and just removing this noise from this particular edge in order to get the original image, yes, we can get it. But I'm not interested in getting the same image. Why is so? Because we are making a generative model. I want that generative model should make an image which is very, very close to the real image, but not exactly the same. If I need to have the same copy of the image, then I will use copy paste rather than making a diffusion model. What I will do? I need to know, my network need to know that what amount of noise we have added on x of, for example, uh, t minus 1 in order to get x of t. What is this amount? For example, this amount is a. I have added x of t minus 1 plus a. I have added this a amount of noise in order to get an image that is called x of t. A or b, any variable that you can assume. I will not tell my model. I will not tell my trained model this is the A. I want to know that I'm interested in training the model in such a way that this my model should be able to get this A, that how much noise has been added in order to get this image that is called XT. How much noise has been added in the previous step is the main objective function of the diffusion model. And if my model is trained enough to get the previous noise, get the noise which has been added in the previous step, then my model can get the image in the previous step. So the target of my network in the reverse process is that he need to know x of t minus 1 given xt. What I need to know? I need to know, given xt, I need to know what is xt minus 1. That means what is the image in the previous step. If we have gone through 1,000 steps like 1, 2, 3, 4, and so on, 1,000, I will again go in the reverse direction to get image at 999, 998, 997, 996, and so on. I think you might be getting the intuition that how can we get image in the previous step? By removing the noise, by removing the noise that has been added in the previous step. Because I know that x of t is equal to x of t minus 1 some noise that is called as a or beta or any variable that you can use just for understanding. So if I will get the value of a, I can get the value of x of t by just subtracting the noise from this particular image. How can we get the value of a? By training a neural network. So the idea of how we are going to use a neural network is totally different from the generative adversarial network. Here the problem is not the classification problem. What is the problem? Which kind of problem we have? Is it a classification problem? In the GAN, discriminator was doing classification, whether it is real or fake. But here, the problem is not the classification, right? The problem is regression. We have to predict the value of the noise. That is the core idea. And how we can predict the value of the noise? For predicting the value of the noise, for making the problem as a regression problem, we should have the label data. Label data means that we should have the value of the actual noise. Yes, we have. For example, x of 100, we have added noise like x of 99 plus a1. And at x of 99, we have added noise like x of 99, 98 plus a2. And x of 98 is equal to x of 97 plus a3. X of 97 is equal to x of 96 plus a4. X of 96 is equal to x of 95 plus a5. So you know the value of a1, a2, a3, a4 and a5. Why I am saying that you know the value of a1, a2, a3, a4 and a5? Can anyone? Do we know the value of noise? Do we know the amount of noise that we have added? No. The answer is no, but actually the answer is yes. Why it is so? Because we have only added the noise. No? We have added the noise with some formulation. Is my voice is clear? Are there a lot of breaks in my voice?
Breaking actually. Somewhere earlier it was breaking in the previous slide, but now it is I think clear.
Okay. Thank you. So we know this noise. Why it is so? Because we have added this noise. In the forward phase, we have added this noise with some formulation. This noise is not added redundantly. This noise was added with some formulation. What is the formulation? That I will let you know. Right now, I am just telling the entire functionality, entire approach of the diffusion model before going into the mathematical details. So what I told, at image at x of 2 is equal to x1 plus beta. This beta is in my control. This is not a random number. We have some formulation, and by that formulation, we have added this noise. Okay, we'll talk about beta in detail. I know this because in the forward phase, we have added this noise. I do know that how this noise has been added in the forward phase. You can just assume that we have an array or we have a vector where we have just stored that how much noise we have added. For example, in the first, in the second, in the third, in the fourth, fifth, sixth, 7, 8, and 9. In each iteration, how much noise we have added. For example, this is beta 1, this is beta 2, this is beta 3, beta 4, and beta 5, or A1, A2, A3 that I have assumed here. So you can just assume at this moment that in each iteration, in the forward process, in each iteration, I have just saved the value or the quantity of noise that I have added because I have used some formulation for that. And no doubt, I will also discuss in detail that this amount of noise that we have added in each iteration, this amount of noise is not constant. We are taking some variations in this, but it is in my control that how much. So we know the amount of noise. Now the problem is now in the reverse process. This is the forward process, and in the forward process, can anyone tell me, do we need any neural network or do we need any machine learning approach to perform this forward processing? Can anyone tell me? Yes or no? In the forward process, yes. I was thinking that might be possible. There may be a little bit confusion in this. The answer is no. The answer is no. In the forward process, what we are doing? We are not doing any kind of prediction or classification. We are just adding the noise. Got it? We are not doing any kind of regression. We are just adding the noise that is x of 2 is equal to x of 1 plus beta. And this beta is simple mathematical variable. It may be a constant or it may be some variable. Generally, this beta is variable. We used to keep changing the value of beta. That I will let you know. And x of 3 is equal to x of 2 plus again beta. So we don't have to do any kind of prediction. We have to just keep on adding the noise in each iteration. That's it. This is the need of the forward process. So again, I'm showing you this image. In the forward process, what I am doing, I am just adding adding the noise in order to corrupt the image. My intention is to just corrupt the original image and make it a pure noise. So we don't need any neural network. We don't need any kind of training in the forward process. But in the backward process, in the reverse process, what I told you, in the reverse process, I need to get this image back. Not exactly, but somewhat similar to. And again this back, again this back. So the intention of the reverse process is to get x of t from x of t minus 1 to get this image. And how can I get this image? By removing the noise that we have added in the previous step. Got it? So again, my second question is, do we need any neural network in the reverse process? Yes. Answer is yes, exactly. In the reverse process, we need a neural network. What is the need of the neural network? Because now have to predict the value of noise that we have added in the previous step, because x of t is equal to x of t minus 1 plus some noise that is called beta, and I have to predict this value. For the same reason, I just plotted these points that data is like this. Data is generated like this. X100 is equal to X99 plus A1 is the amount of noise. X99 is equal to X98 plus A2. X98 is equal to X97 plus A3 and so on. In each step, we have added some noise. We have saved the amount of noise that we have added in each iteration. What will happen in the first step in the reverse? For example, we are going through 100 iterations. We have corrected the image in 100 attempts. Then the question is, yeah, this is a very good question that someone has asked me, that if we know the value of noise that we have added in the previous step, then what is the need to predict the noise? Exactly. I have already told you that if we'll keep on removing the same amount of noise, because we have put the same amount of noise from this image, again we have removed the same amount of noise that we have added in the previous step, then what we will get? Just answer me. We will get the actual image, original image. Yes, we will get the original image. But which model I am making? I am making a generative model. I'm not interested in just copy and paste. We can just copy and paste 100 times to get the original image. Na? So in the case of GAN as well, we have given the input of 100 faces. But What is my expectation? What was my expectation from the GAN? My expectation was to generate the duplicate faces. Original faces we have. So same, because we are making a generative model. So in future, I want to train my model in such a way that it should be able to generate the images with itself after the training. So exactly, you have also got, you already got the answer. So what I will do, my model will just, I will train the neural network. Which neural network we may take? Generally, we take unit kind of model. Why we take unit kind of model? That is another question that we will discuss later. Yeah. So my neural network model is going to predict this value of A1, but it cannot predict exact value. So my neural network will predict that, yeah, in the previous system, you have added, for example, you have added A1 at, this is the quantity of noise that we have added. We have the actual noise. This is the predicted noise. This is the actual noise. What is this? This is predicted noise, and this is the actual noise. What is the loss? A hat minus A. We can take mod of this. So this is the loss. And if this is the loss, fine. Again, for the previous step, for the 99, my model is to predict the value of A2. It will give A2 hat. We have the actual loss. That is called A2. Again, for one more previous step, A3, my model is going to predict the loss, that is called A3 hat. I have the actual A3. Got it now? So what will be the over loss for all loss for one particular image, for a particular image? Anyone tell me? What will be the overall loss? Sigma. Exactly. Exactly. Yes. Yes. Sigma. Addition of losses of all the iterations. Exactly. Exactly. You're getting it quite clearly. That means if I am taking in a general way, that is A of I at minus A of I. So it has to be summation of losses of all the iteration. So that means one more thing. What is that more thing? That more thing is this process is computationally complex. So in order to complete one iteration for a particular image, we have to predict the losses 1,000 times. If we have corrected the image in 1,000 steps, we have to predict the loss 1,000 times in order to get the overall loss for a particular image. So no doubt, if we compare the computational complexity of this process, of this model with the generative adversarial network, then the answer is that the diffusion models are more computationally complex as compared to the generative adversarial network. Okay, now we have this loss, and if we have this loss, means we have some supervision. Getting the loss, that means we have some kind of supervision, that this is the amount of deviation that you are getting. Need to, then what we will do? We will need to back propagate. We need to update the value of weight and bias. What we are going to do? In the reverse phase, my model will get some training in a supervised fashion. Why supervised? Why in a supervised fashion? I am saying because I am also telling my model that this is the amount of noise that I have added. Now you need to predict how much noise I have to add it. Whatever the difference is, that will be the loss. And my model will try to reduce the value of loss as much as possible to make the image more and more realistic. Again, coming to the point, I now expect that you have got just a nutshell of the process, that how this particular image is being deteriorated in the forward phase, and how this particular image is getting back in the reverse phase. This is the overall nutshell story. Now I will just give a step-by-step explanation that what we are doing and how we are doing in detail. So let us see. Exactly. Coming to the definition, what are diffusion models? Basically, these are the generative models that generate high quality data by adding and reversing the noise. Yeah, the point is quite clear that they are able to generate high quality data by adding the noise and reversing that noise. Before, if I had started with the same definition before telling you the entire story, then might be possible you may not have got the point. But I hope naturally you have got the point, that how these diffusion models are able to generate high quality data by just adding the noise and by reversing the noise. Again, I am repeating the same point that from where I have started, that what generative adversarial networks do, they start with a random noise and they try to mimic the data distribution of the original data with the help of the discriminator model. Here, we start with the random noise, but that random noise has been prepared from the original image by adding the noise systematically, step by step. If we have corrected that image in one step, then it was very difficult for us to get back that exact image. I hope you have got that mathematical intuition behind it, that why we have added noise step by step, not in one go. So yes, how they work? They begin progressively by adding the noise to the data set. We are quite clear with this, and learn to reverse the noise addition process to reconstruct or transform the data. The same that we have discussed. That this model, what is the learning? What is the training process? Training process that to learn the reverse noise addition, that in which way to learn the pattern in which way the noise was added in the image in order to get back the same, not exactly the same, rather similar image, because we cannot predict the exact number. We will always have some loss, 2%, 3%, or 1%, and by so the regenerated image will be similar but not exactly the same. What is the key concept? Key concept is gradual degradation of the high quality data. The gradual degradation of the data, not always high quality, followed by reconstruction to its original form or in the new form. And what is the result? Result is highly detailed and accurate outputs. And this particular diffusion models are applicable to all kinds of data, whether it is image or it is a text sequence or text to image translation or whatever it is. By the course of time, this model has been advanced in such a way that it have quite larger capability uh, uh, to have dehaze the image, to just blur the image, to just increase the resolution of the image. In all the ways, researchers have tried to just tune or just to update these diffusion models. And not only the researchers, bigger companies like Meta, Google, and other companies have just made their own models, made their own tools in order to have better understanding of the ideas, in order to generate high quality results. Now, what are the applications of these particular diffusion based models? Naturally, to generate real time or realistic images from the random noise. And the applications of these diffusion models are more or less similar to that of GAN model. For example, if you want to create some scenes, if you want to augment the data for the minority cases, then we can also use diffusion models as well. So we can have the images generated from the GAN, generated from the diffusion-based models in order to get some samples for the minority classes, if you want to train our model in a good way. So that we have already discussed. Now coming to the points step by step that we have already discussed in nutshell, that how diffusion model works, that we have already discussed that diffusion model works in two phases. One is the forward phase and one is the reverse phase. In the forward phase, we used to keep adding noise, beta 1, beta 2, beta 3, or A1, A2, A3. And in the reverse phase, we have to just remove this noise step by step in order to get the original image. Multiple steps. And this is quite important. We have to add the noise in multiple steps. Might be possible. One question again be coming to your mind, that why we are, if I wanted to capture some image, why we are adding noise slowly and slowly and in step by step, why we are not able to just add the noise in one go and corrupt the image. So the reason is we need to know how much amount has been added in step by step, because we need to predict in the reverse phase. Hope this point is clear to you. So see, naturally, this process gradually degrades the data, turning the image into the random noise that we have already seen. And the goal is to make uh, data increasingly noisy until it is almost unrecognizable. We will keep on adding the noise, and number of steps is not always fixed. So in this example, I have chosen the value of t is equal to 1000. Generally, 1000 steps are sufficient to make any image unrecognizable, but it is not always the case. It also depends upon the quantity of noise that you are adding in each step. So if you are adding very less amount of noise in each step, then naturally you will be needing more steps in order to get the image almost unrecognizable. But if you are adding some more or some uh, good quantity of noise in each step, then it is going to take uh, less number of steps in order to get image quite unrecognizable. The idea is quite clear. You have to get a balance between the amount of noise that you want to add and the number of steps that you want to choose. Reverse diffusion phase, that means we have to train a neural network to reverse the noisy process that we have already discussed. In the forward process, we don't need any neural network to train. Why it is so? Because the aim of the forward process is just to add some noise. We are not in a need to do any kind of regression or classification kind of things or any connection kind of things. But in the backward process, we need to know the quantity of noise that has been added in the previous phase. So we need some prediction model. So that's why we need to train a neural network in the reverse process, and the model learns to denoise data step by step, essentially to recover the data and transform it to the new form. Yes, that we have already discussed, that learning to reverse noise, that we have to train our model in such a way that it should learn that how much noise has been added in the previous step in order to get the detailed high quality data and realistic image. Now coming to the mathematical part. So far I have just told you that we have to add some noise to the original image in order to make it noisy, and we have to keep on adding the noise in step by step in order to make image unrecognizable. But now we will see the mathematical equation behind it, that what should be and how the noise should be added to original image in order to get the corrupted image. This is also, this step of adding the noise is somewhat similar to Gaussian distribution. We use normal distribution or Gaussian distribution to add the noise. So you just see the equation q of xt minus 1. That means given xt minus 1 and I want to get xt. That means given image at x of 99 and I want to know the image at 100, iteration number 100, or given image at iteration number 1, I want to get the image at iteration number 2 in the forward process. So this is t minus 1 and this is xt. This is the data in the next iteration and this is the data in the previous iteration. So this is the equation of Gaussian or normal distribution, that I want to get xt by adding this much amount of noise. So in the Gaussian distribution, you already know that Gaussian and now these are Gaussian distribution is something like this. Someone has asked the distribution like, what is Gaussian? Gaussian distribution is something like this, or normal distribution or Gaussian distribution. So this is the mean. Generally, the data is distributed around the mean. Majority of the data is distributed around this, that is called mean. So Gaussian distribution have 2 points. I think I have already told in the previous session. That is mu, mean, and standard deviation, sigma. So mean tells that around which point the data will be distributed, and standard deviation tells that what will be the deviation in the data that you want. Got it? So for example, I have given standard deviation as mean as 8 and standard deviation as 2. So that means the average of all the data points that I have generated will be around 8, and all the data will be distributed with a standard deviation of 2. More will be the standard deviation, more will be the scattering in the data, and more will be the value of mean, more will be this peak. Got it? So this is mean and this is standard deviation. In this the original paper, this factor, that is standard deviation, was kept constant. We are not varying it. Whereas this mean is actually dependent on, this factor is dependent on beta t. So this beta t is actually not constant in the original paper. We used to just change the value of this beta t, and the amount of noise that we add in each step is actually dependent on beta t, and we have two choices: either to keep this beta t constant or just vary the value of beta t with the course of iteration. For example, if I am keeping the beta t constant, that means in each step, if the value of beta t is constant, that means in each step we are adding the same amount of noise. However, if the value of beta t is not constant, that means in each step we are varying the amount of noise in the in order to corrupt the image. So it is also written here. I have explained all the things in the PPT for future references. It is clearly written that beta t is a variance controlling how much noise is added in each time stamp. So beta t is going to control the amount of noise in each step, and naturally xt minus 1 is the data from the previous step, and x of t is the data in the current step. We are going to get the data in the current step by adding some noise in the previous step. And capital T, what will be capital T? Capital T is the total number of iterations. Total number of iterations or steps. Total number of iterations or step means in how many steps I want to accept the image. So for example, the value of t I have chosen as 1000. So that means 1000 steps I want to accept the images. In each step I will be keep on adding some amount of noise, that is called as beta. Got it? This is the basically Gaussian distribution that we have, similar to Gaussian distribution that we have also taken in the case of generative adversarial networks. Here is also, in order to get xt, we have to add the noise with this mean and this standard deviation. No doubt this step is going to be changed. The value of beta has to be changed dynamically with the course of iterations. Now, this is the answer of the question that has been also asked in the first slide, that is the amount of noise same in all the iterations, or is the amount of noise different in all the iterations? So I have already answered that yes, the amount of noise that we are adding in each iteration is not same. Rather, exactly, exactly. Rather, the amount of noise that we are adding in each step is varying. So how we are varying the amount of, how we are varying the value of beta with the course of iterations? It is not always pretty fixed that we have to choose this mathematical equation. But uh, at this moment, I am just telling you what originally in the vanilla diffusion model was made and how the value of beta was changed. You can have your own mathematical equation to just vary the amount of noise that you want to add in each iteration. It is not always this same for all kind of data distribution. So again, the freelance theorem came that says that it is not always necessary that you will, all kind of diffusion models are going to perform uh, good for all kinds of data. So you can have your own choice. But in the original paper, authors have just t is equal to 1000. That means they have corrected the noise in 1000 steps. And starting value of beta s was chosen as 0.0001. This was the starting value they have chosen. You can assume that these are the value of some kind of parameters, and you can just fine tune your model. If you are developing your diffusion model for your own requirement, you can just change accordingly. And beta end. So this is the beta start, and this beta end was chosen as 0.2. I'm talking about the original diffusion model paper. At the end of the session, I will also share the original paper that I'm explaining here. And generally, that paper is used as a reference to just understand the functionality of the diffusion model. And if you want to have your own research, you can just have your own neural network. You can have your own choice of beta variations. So you can get one some idea that how we can just vary this beta by the course of iterations in order to add the noise, in order to add the variable noise. This is the value of beta start, and this is the value of beta end, and this is the total number of iterations. What they have did, they have just linearly changed the value of beta by the course of iterations. We can have our own method. We can just change the value of beta exponentially. If you are changing the value of beta exponentially, that means you are adding more and more noise at each iteration. If I want to change the value of this beta linearly, then what we can do? We can just define that beta at any time stamp t. It may be equal to beta start plus some factor. And what is this sum factor? This sum factor is t cross beta at the end minus beta at the start divided by capital T, where beta end is the you can say this is the max value of beta that I'm picking, that is 0.2, Beta start is the minimum value of beta that I'm choosing, that is this. You have to define the start and end. What is T? Yeah, T is the total number of iterations. Total number of iterations. What is small t? Yes, small t is the current iteration. Small t is the current iteration. So, for example, I want to know beta at 10. What will be the value of beta at 10? Beta start, that means 0.0001 plus current iteration number, that is 10, into beta end, that is 0.2, minus beta start, that is 0.0001, divided by t, number of iterations, that is 1000, like this. So, have you got mathematical intuition of beta t, that how beta t is basically changing, whether it is increasing or decreasing by the course of iterations, and how it is increasing or decreasing? Yes, yes. So that means this beta t, I have got the intuition that this beta t is increasing linearly, increasing linearly. So this beta end is fixed, this beta start is fixed, total number of iterations is fixed. What we are changing? We are changing the iteration number. So this is some fact. This is some fact that is very, very small, no doubt. We are multiplying this fact. We are adding this factor in the start value. That means what we are doing, we are just increasing the value of beta from 0.001 to 0.02, from this point to this point in linear fashion. So what does it mean? It means that are we adding less amount of noise in the initial steps and more amount of noise in the later stage, or vice versa? Are we adding corrupting image? Uh, yes, you have got the point. So that means we are at the initial steps, we are adding less amount of noise, but in the later on steps, we are adding more and more amount of noise, because in the reverse process, no doubt it will be very difficult to just retrieve the image in the last momentum to get it more and more precise. So no doubt it is not always the case that you are bound to take these values of beta. It is not always the case that you are bound to increase the value of beta linearly. Actually, these things depends upon the hit and trials. Uh, uh, when we are developing some new model, we try to just change these value of parameters uh, to get more and more accuracy, to reduce the amount of loss. And no doubt it also depends upon the data. If you are making your own model, you can have some kind of experimentations that how this beta should be changed. This is also one of the scope. This is also one of the scope for the researchers. If you are making your model, so I'm just discussing, this is the scope number one, that how you are changing the value of beta. If you are able to if you are able to introduce if you are able to introduce some new equation of beta by which your results are getting improved, then no doubt that will be some kind of novelty as well in your research work. So we are not only thinking, as soon as the model is being introduced, everyone start thinking that how we can just improve the model. So as soon as in 2020 this paper came out, some researchers had already tried some of the mathematical models, some of the mathematical equations that can be used in order to change the value of beta. So let us also see that what is the impact of changing the beta on the original image, because the way in which you will add the noise is going to teach is going to give the label the way in which you uh, uh, get your model back. Okay, so just see this image. These are some of the methods that has been already explored in case of for changing the value of beta. So just see, this is the if we are changing the beta linearly, then this is the way we are getting the image. We are using cosine functions. So this is the way in which we are corrupting the image. And if you are using sigmoid function, image is corrupted in this way. If you are using exponential method, then this image is corrupted in this way. So naturally, these are some of the methods that has been already explored for changing the value of beta. However, you can have your own method for your own data set in order to change the value of beta. Now, this is the same thing that we have already explored that, in the original uh, paper that has been introduced. This beta was starting with this. It is not always mandatory that you have to pick this value of beta. And this was the end value, and total number of iterations was a capital T. And this eventually reaching the value that makes the data indistinguishable from the original one. But in the original paper, this value of beta, this variance in the original paper, this variance was kept fixed, because if you are also changing the variance, then you will be needing one more neural network to just predict the variance that we are making in each step. So we are not discussing about the same. The only thing is that how this is varying. If I am going from x1 to from x0 to x1, this is the equation that if you want to get x1, what is the impact? Yes, definitely. Actually, the amount of noise that you are adding makes the labels for the reverse process. For example, you are adding some value that is called beta 1 in the first step, that is x1 in the second step. The way in which you are correcting the image is going to help the neural network that you have trained during the reverse process. So generally what happens initially, if you are corrupting the image with less speed, and later on we are corrupting this image with more speed, generally helps the model, because at this moment of time when you are in this stage, it's a very crucial stage that how accurate image we are getting. So here what we are doing, we are just adding some less amount of noise in order to have kind of better exploitation at this moment, kind of. So in the later stage, in this territory, in the later iterations, I want to have some good jumps, and in when I'm coming close to the when I'm coming close to the original image, that means we have to exploit well here. So keeping in mind, might be possible that author have just kept the value of beta less in the starting stage and more in the. So no doubt it is a matter of, again, this is a still a matter of research, that what should be the value of beta in the starting and ending, how you should change the value of beta from starting to ending. It is not any rule, any not a mathematical rule. It is just empirically validated that if we are increasing beta in this fashion, we are getting good result, but this is not mathematically verified. So again, this is a question of open-ended question for the research, that how to choose the value of beta wisely and how to change with the course of iterations. No doubt, in future you can also change this variance as well. That what should be the variance with the course of iterations in order to change the probability distribution. But again, these are still the questions of research that you can just explore. Now, if I want to make, if I want to just get in back and get this original equation, that x1, if I am just replacing this x0 with x1, what I did, I just keep this value, that this x2 will be 1 minus beta 2 of x1, and again if I want to know x3 given x2, that will be equal to x3 this root of 1 minus beta 3 x of 2 beta 3 of I, like that. But if I want to just simplify our mathematical intuitions, that we can also replace alpha t with 1 minus beta 2. So I am assuming one more uh, variable that is called alpha of t. Alpha of t is equal to 1 minus beta of t. It is reverse of that. For example, beta t, what beta t represents? Beta t represents the amount of noise that we are adding to image. So naturally, what alpha t will represent? Alpha t will naturally represent, because it is just reverse of that. I am just normalized my data from suppose 0 to 1. If I'm talking about the probability distribution kind of thing, if I have just normalized my data from 0 to 1. So in that case, what alpha t will represent? Alpha t will represent the amount of data that we have, yeah, or the amount of information that we have in my original image. So for example, if the value of beta is, for example, 0.05 and the value of alpha is 0.5, so that means we have 95% of the data and 5% is that of noise. So alpha is representing the data and beta is no doubt representing some kind of noise. So what I did, I did nothing. Not exactly I, rather what was did in the paper. That is, they have just replaced this alpha with beta, beta with alpha. That means alpha is equal to 1 minus beta. So alpha will come here. So in order to make this simple, so it is something like alpha 1, this and this. So mean will be equal to root of alpha t x of t minus 1. So again, if you will keep on just retrieving it, if you apply some kind of mathematical inductions, so what will happen? What will happen here? This will be, I'm replacing this alpha t with alpha t minus 1 in this. So this will become like this. And again, if you are replacing alpha of t minus 1 with alpha of t minus 2, so we'll get the equation like this. So I think this is a quite simple mathematical equation, that if you will keep on just changing it. Someone is talking about this. What is this? This is kept constant. You just assume that this is a variable that can be varied with the course of iterations if you want. But here in this case, I am just keeping this constant. That's why I am not discussing about this variable. But this is something which can control your standard deviation. So this variable can control your standard deviation in future. But at this moment, I am not changing my standard deviation, or in the original paper, the standard deviation was not changed. That's why just assume this as a constant variable. Okay, that's why I was not discussing about this variable. Got it? So this, if I want to just generalize it, I will just keep on expanding it, and if I want to generalize it, then this alpha t will become equal to product of this from iteration 1 to iteration t, like this. So this is the value of this is the mathematical intuition behind it, if I want to just make it in a generalized way. If you want to just generalize it, we can do it like this. We can have some kind of variable that can be used to uh, corrupt the noise in in single way. It can help us to corrupt the noise in one attempt. But how we are able to do so? Because we have made this mathematical equation, we can just retrieve that how much amount we have just added in each step. No doubt, it is not our matter of interest at this moment. You can just ignore this one. It was just used to make our mathematical equation somewhat generalized, but you can just ignore it at this moment if you don't want. Okay. Intuition of the forward diffusion process that we have already discussing from the very first slide, that intuition of the forward diffusion process is to just degrade the image slowly, step by step, so that we can just retrieve the image in a similar way in the backward direction. Now let us visualize. This is quite important. whatever the mathematics and whatever the intuition we have learned so far, we need to just visualize that how with the course of iteration the forward diffusion process is going to take place. So what theoretically we have studied, I am just going to show you step by step how the original image is being corrupted by adding noise in each iteration. Let us see in order to have better visualization of the fact. At timestamp t equal to 0, I am taking this original image like this. And in the code, similarly, I will show you the output while performing the hands-on in the next session. I will give you a code and a notebook. You will run it, and you will be able to show the images which has been generated by the diffusion model. So you will be able to just check the intermediate uh, outputs that are being generated in the diffusion process. So before that, let's visualize it. At t equal to 0, my original image is like this. Ultimate aim is to generate noise for current step t. So for example, I have generated some noise using variable beta. And this noise distribution is, how is the noise distribution? Gaussian distribution or normal distribution. What I did, I have generated this noise using Gaussian function, and I have added this noise in the original image. This noise is being added to the original image, and after the first epoch, I have got the image like this. Just to visualize that how diffusion models work. Original image developing the noise of the same dimensions. I have already discussed that how to just create a noise vector, and after creating a noise vector, we can have some reshape layer and dense layer, followed by the convolution 2D layers in order to make this noise vector. So we can just create a 1D noise vector, and then we can just reshape it according to the image dimension, reshape it according to image dimensions. Got it? And after reshaping it, I will just add this in order to get this image. This is timestamp t naught is equal to 0. So what will happen? This is the output image after equal to t plus 1. Now let us see whatever the output image that has been generated. So this is the output image. This output image will become input for the next iteration of forward diffusion process. Forward diffusion process. So again, what I'm taking, this is iteration number 1, and this is the input image for iteration number 1. And from where this input image came? This input image came after adding some noise to the original image in timestamp equal to 0. Again, what I will do? Again, I am generating this noise. Now you are also image using linear scheduler. Now you have got the point. What do you mean by linear scheduler? That means this noise vector that I have created at timestamp t equal to 0, this noise vector that I have created at timestamp t equal to 1, is both the noise vector are same or different? The noise vectors that I have taken at t equal to 0 and the noise vector that I have taken at t equal to 1, is this noise vector are yes different? That means you are getting the point. Very good. So it is different because we have changed the value of beta linearly. That's why we are adding different quantity of noise in each step. No doubt at this moment, what I am doing, I am increasing the amount of noise in each iterations in order to correct my image. Or reverse process में what I need to do, I need to just predict this. I need to just predict this noise in the reverse process. That is the actual problem. Next, let us visualize more. This is t equal to 2. What we have done, whatever the image that we have, generated at t equal to 1 will become input for t equal to 2. For the second iteration, let us see. This is the image that we have generated in the previous step. Output from step t will become input again, and the whole process will repeat. This is again a noise vector. And just see this image and this image, that is the image at t equal to 1, and this is image at t equal to 2. Both the images have some variation. It is a little bit more correct. And this is the noise vector that has been reshaped in the dimensions equal to the original image. For example, this is 64 cross 64 image. So I have reshaped my noise vector in 64 cross 64 in order to add the pixel values. Okay, equal to 3, t equal to 4. Again, this is the image at t equal to 3. This is the image at t equal to 4. This is the noise vector that we have developed, and you can see that the noise vector, although the differences will be quite less, but the noise vector that I am generating at t equal to 1, t equal to 2, t equal to 3, all the noise vectors are different. They are having different values, and they follow the Gaussian distributions that we are taking. All the noise vectors are following the Gaussian distribution. Good. 5 again. Now we can see that this is the image at t equal to 4. This is the image at t equal to 5. This is the noise at t equal to 5. Now we can see that in this image we are not able to I'm not saying that in 5 iterations I will just correct the image. So you can say that we are the taking image sample set in 100 iterations. Here one iteration is equal to 100 iterations. 100 actual iterations you can assume. Image is looking like this. T equal to 6, more noisy. T equal to 7. Now you can see this is the noise and this is the noise, and again I am getting a noisy image. T equal to 8. Now you are not even able to recognize that which is the input and which is the output image and which is the noise. 9. So in the last step, what I have assumed that t one iteration is equal to 100 actual iterations. So after 1000 iterations that are equivalent to 10 iterations that I have taken, this initial information is completely destroyed. Now this is the 1000 times steps for the forward diffusion process. This is the image at t equal to 0, then 100, then 200, 300, 400, 500, this and this, 600, 700, 800, 900, and 1000. I think you are able to now visualize that what is the basic difference between the plan and the diffusion models. In the generative adversarial networks, we started with pure noise, and this pure noise was not generated from the actual image. Rather, it was totally generated from the random numbers. But here, in the case of input training data, we also started with the noise, but this noise has been created using the original image. We have got this noise from the original image. So the key ideas of GAN and diffusion models are totally different, and no doubt Can you now answer that? Which model is computationally more complex? Anyone? I have already told you in the beginning of the lecture that which model is computationally diffusion models. Exactly. Why it is so? Because in the reverse process, I need to just uh, pick the noise at. Yes, I in the reverse process, I need to predict the noise at each iteration. So for each image, I have to perform the same task 1,000 times. That is not in the case of the generative adversarial network. But as a matter of fact, in majority of the applications, diffusion models are able to outperform outperform the GAN models, that is called generative adversarial network. Why it is so? Because we are giving some kind of uh, input hint to the generative adversarial to the diffusion models. So this is the case, and if you have any queries till now, you can just ask me. Otherwise, we will take a break, and I will start new session from 11:30. So meanwhile, if you have any questions, you can just ask me. Otherwise, you can just have some a little break. I will resume my next session at 11:30, where I will resume this from the same point from where I am leaving this. And in the next session, I will be also giving you some code which you can just look and just execute it and just see that how the diffusion model is basically generating the intermediate outputs, and how the diffusion models is basically able to just create the new images. Moreover, that particular code will be having 5 to 6 data sets on which you can just train your model. You can just also trying to change the value of beta, and the neural networks that I'll be using for the reverse process. You can do some kinds of hands-on, some kinds of hit and trials. You can try some different permutations and segment combinations if you are able to just outperform the existing models naturally. So okay, let's take a break. We will just meet at 11:30, and I will continue from this point only. And after that, I will also be discussing about some of the audio video generations, that how we can just generate audio and video, and what are the existing state of the art models for generating an audio and video, which can be helpful for you in future. So we'll meet again at 11:30.